All right, let's talk about the biological buffer in our body, right? In any living system, the buffer in our body is actually the carbonic acid and bicarbonate system. That's our buffer. So there's an acid form, that's a basic form. Okay. So if you look at the whole equilibrium right here, carbon dioxide can react with water to make carbonic acid. Carbonic acid dissociate to make hydrogen carbonate and a proton. Can go all the way there and go all the way back. They are all in equilibrium. Okay. Now, when we exercise, all right, when we exercise, this is how this buffer system works. When we exercise, we generate lactic acid. That's why parts of our body hurts because of lactic acid. And lactic acid is an acid make more higher concentration of proton, right there. Right. When our body have a higher concentration of proton, well, the pH of our blood is going to change, right? When we can't let that happen, the buffer have to go to work. Who's going to come pick up the proton, the acid or the base? The basic form. So the hydrogen bicarbonate will react with the proton that from our activity to make more hydrogen carbonate, right? And the hydrogen carbonate will break down into carbon dioxide and water, and too much carbon dioxide in our blood, we have to get rid of it by by panting, by exhale. That's why when you do exercise, you're breathing really hard, you're panting. So our body try to get rid of the excess carbon dioxide from our activity. And this carbon dioxide come from the buffer solution when it goes to work, right? Because acid react with hydrogen carbonate, make carbonic acid, and in equilibrium with carbon dioxide. So we basically, when we exercise, we have more carbon dioxide in our blood, and our body have to get rid of it by exhaling faster. Okay. All right, that's how our body works, how the buffer solution works. All right, which of the following solution can be classified as buffer system? Explain your answer. A, can it be buffer system? Well, if you remember, the buffer system have to come from weak acid and its conjugate base. Cannot be a strong acid. Okay. All right. So if we the first system we have phosphoric acid and dihydrogen phosphate. So phosphoric acid and hydrogen phosphate. If you add an acid, who's going to come pick up the acid? The basic form, so dihydrogen phosphate, and become phosphoric acid. If this solution got added a hydroxide ion at the base, the acid form will go pick it up and become dihydrogen phosphate. The pH doesn't change. Okay. All right. Try the second one right here. So we have perchloric acid and in equilibrium with sodium chloride, sodium perchlorate. Okay. So they are in equilibrium. But you know, perchloric acid is a strong acid. So this is not, totally not. But I'll show you explanation right here. When you have a strong acid, right? If we add an acid, who's going to come pick up? The base, right? So if they say add an acid, the base come pick up the acid. Perchlorate will become perchloric acid. What happened to perchloric acid? Does it stay as a molecule? No, strong acid doesn't stay as a molecule. Dissociate right away, make more proton. So basically, this proton has no one to pick up. So this solution cannot withstand the pH change from adding an acid. See that? Lastly, so we have ammonium chloride and ammonia system. So ammonium ion, that's the acid form, and ammonia, that's the basic form. Well, that's okay. The arrow is wrong. So ammonium ion is a weak acid. I supposed to use the equilibrium arrow, not the one-way arrow like that. So this is wrong. It's supposed to be equilibrium arrow. Okay. All right. This system works because when you add an acid, ammonia will come pick it up. If you add a base, ammonium ion will come pick it up. And pH doesn't change. You know that? Yep, that's how the buffer solution works. I hope it helped you a little to explain this. Okay. All right. Let's moving on to one.